will be presented by Professor Schnack, Jurgen Schnack from University of Bielefeld. So it is about high-spin molecules and molecular magnets. So Professor Schnack, please.
Yeah, thank you very much for the kind introduction. I'd like to give a short presentation on some recent work that deals with the influence of spin-phonon interaction on the tunneling gap of single molecule magnets. And I'd like to address the following two questions today. First, can spin-phonon interaction open a tunneling gap or induce a tunneling gap in systems where there was no tunneling gap without spin-phonon interaction? And then the second point is more driven by curiosity. There are interesting phonons that are kind of innocent or induce unusual behavior in single molecule magnets. But before we come to that, I'd like to start with an introduction. So my talk will be a theory talk. And I'd like to remind you that we need for single molecular magnet behavior, we need anisotropic Hamiltonians. The Heisenberg Hamiltonian that we very often deal with alone cannot induce such a behavior. So we need a Hamiltonian, as given here above, where we have, for instance, in this model, a term that describes both the exchange given by the exchange integrals here for each pair of spins at sites I and j in a magnetic system. There is a 3x3 matrix, potentially, that describes the isotropic as well as anisotropic exchange. And then if the indices I and j are the same, then this is called the single ion anisotropy. And of course, we investigate systems usually by applying an external magnetic field. And therefore, we also need a Zeeman term describing the interaction with the external field. Okay, and if we boil this down to a very basic and simple system, then we might deal even only with a single spin. So this could be the ground multiplet of a larger system, but it could just be a single spin. Imagine a manganese 3 ion or chromium or so, with some spin quantum number S, and of course magnetic levels given by the M quantum numbers. And a very basic model for our understanding of single ion anisotropy is given here by this Hamiltonian. The first term describes the easy or hard axis of a single spin. That's basically given by the square of the Z component of the spin operator. And of course, we again can apply a magnetic field, and let's apply it into Z direction. So these directions are the same, and this is very important. So if D is smaller than 0, we call that an easy axis. Why? You see this when looking at the spectrum. The spectrum is easy to derive because this operator depends only on Z operators. So the eigenvectors of the Z operator are also eigenvectors of the Hamiltonian, and we can immediately write down the energy eigenvalues. And for zero field, they form a perfect parabola as a function of the magnetic quantum number. And you see that if D is negative, we have a ground doublet given by the maximum possible M quantum numbers. Yeah, in this case here, -3 and 3, I mean, fictitiously. Okay, and what is very important is that the Zeeman term commutes with the remainder of the Hamiltonian, and this leads to the fact that if you apply a field, these two lowest levels given by the n plus minus 3 here in this case, these two lowest levels, they cross at zero field. Whereas when you add another term to the Hamiltonian, namely this one here called the E term, which is the other given by the other two components of the anisotropy tensor. So if you add this term, then you immediately see there are components that do not commute. Okay, for instance, you could consider the D and the Zeeman term here, and they don't commute with that one, or you take this one and then it doesn't commute with the SZ. So these cats here are no longer eigenstates of the Hamiltonian, and the eigenvalues are more complicated functions of the applied field. And since the Hamiltonian does not commute with the Zeeman term, what we observe here for integer spins, one must say, is a so-called avoided level crossing at zero field. Yeah, so you have got level repulsion at zero field. In case of half integer spins, there's of course Cramer's degeneracy and you can't avoid the crossing. Okay, but for integers, there is no crossing. Now, why is this important? Well, this is important because we want to use the single molecule magnets as storage units. And for this purpose, we need bistability. And in a uniaxial system, so where everything points in a z direction, for instance, with a single spin, or if you have more than, say, with ferromagnetically interacting spins, you need this symmetry in order to remain in a given Zeeman level up to a certain field. And then, of course, due to other effects, phonon and so on, you would jump down. But you need to stay in this level in order to achieve a hysteresis. So you want, even at b equals 0, remain at a certain magnetization, and you would like to be able to achieve this bistability of the two stable magnetizations at zero fields. Okay, and this, of course, also the case in macroscopic magnets, but there the time is huge. That these things would relax. Okay, so but this is the goal, to have bistability. And now if you have got a system that has not as an SZ symmetry, for instance, like given with this Hamiltonian, so you have the single ion anisotropies and the Zeeman term, and say some ferro interaction between ions, and if this is not uniaxial with SZ, then, as I told you, we observe this avoided level crossing. And this destroys bistability. What happens now is, depending on how quickly you ramp up your field, you run along, say, for instance, for very slow, slowly increasing field, you run along, say, adiabatically this lowest level, or if you're quicker, you jump up to this, and anything in between, so partially occupying these levels, and this is all known thanks to Landau, Zina, and Tsukerblat. But what it means is that if you say you start at negative field and you ramp up the field slowly, what happens is you don't have this perfect hysteresis, but since you remain in the lowest level, at least to some part, you destroy the hysteresis. And if you approach b equals 0 very slowly, then you might even observe no hysteresis at all. So what we have is a strongly time-dependent hysteresis that may even close at b equals 0, and we don't have bistability. And that's it for the introduction. The state of the art, from my point of view, today is given by the following points. So what one wants, and I didn't address this very much, one wants ferromagnetic spin-spin interactions between the centers of a molecule. Okay, and this is as one point that's very hard to achieve. Then if one has got a system, what one wants is uniaxial anisotropy tensors. And for instance, in this molecule here by Thorsten Glaser, this is a sketch of a manganese 6 chromium. The anisotropy easy access of each manganese, they are not collinear. Okay, and this is very bad. This automatically opens a tunneling gap. Okay, and then what would also be very nice and is very important today is you want to achieve a symmetry in the system that does not permit any E terms or terms that do induce a tunneling gap. Okay, all these very nice and modern dysprosium whatsoever single ion magnets, they have very strange symmetries. D5H, Boris, you know this better than me, but you know, strange symmetries that do not allow tunneling. Okay, it's very hard to achieve, to have proper control of a perfect symmetry, but this is definitely the goal. Okay, let's assume we know this and we try this. What remains open and is the topic of this talk is the spin-phonon interaction. And I want to start with an approach that I'm not going to follow, okay, but that might be familiar to many of you. So what's the usual approach to phonons? Well, the usual approach is that you consider phonons as some disturbance, like in scattering theory, that induces transitions. Okay, that's the normal picture of phonons. So say you have again the spectrum of our single molecule magnet here, and then the phonons, they induce transitions. And there are very advanced programs today to calculate this effect. So you can calculate the structure by means of DFT, for instance. Then you can calculate the phonon density of states by means of DFT and molecular dynamics. So there are some examples given here by the references. And then you can even calculate the spin-phonon coupling coefficients also from DFT. And what you then do is what I mentioned, namely, you've got the idea of scattering theory or perturbation theory, namely that the phonons induce transitions, and then you set up rate equations for the transitions induced by phonons between eigenstates of the otherwise unperturbed spin Hamiltonian. Okay, there's a certain advantage of this approach. You have many realistic phonons, and you certainly cover this aspect of transitions. Okay, but there's also something missing. Yeah, the phonons, they are not part of the quantum system that you described. They come in like in scattering theory asymptotically. But there are different approaches, and that is what we were interested in, namely to treat the spins and vibrations on the same footing, say in a Hamiltonian. And it's clear to the experts, at least when I say this, that you can't treat many phonons, okay? Because your Hamiltonian gets huge and your Hilbert space enormously large in an instant. So, but the question we wanted to answer, you can address, I would say, actually with a single vibrational mode or so. So we were wondering whether phonons can induce tunnel splitting. And to this end, we looked at a system that has, say, C3 symmetry, so say a triangle of 3 ions, imagine manganese 3 or so, with strong easy access, okay? And our idea was to look at a system where the easy access without phonons are collinear. So this would be a perfect single molecule magnet, but then allow a phonon mode that tilts the easy access away from uniaxial, okay, in a C3 fashion. So we keep the symmetry. They are allowed to move outwards and inwards, but relative to each other by an angle of 120 degrees. So we can write this Hamiltonian down. You see that on the next slide. And we can work in a Hilbert space where we have the magnetic quantum numbers and the phonon numbers. It's clear that you have to truncate the Hilbert space because you have so many phonons. You truncate this at some number of phonons per mode. And if you now look at this level scheme, you see that each magnetic level is of course split into many due to the phonons. Okay, you have a multiplication of an increase of levels, and if you would have many phonons, they would turn into bands certainly. Okay, this is the Hamiltonian. Don't be frightened. This is a simple Hamiltonian. Okay, I guide you through. The first term is the Heisenberg interaction between the three spins in the triangle. 1 with 2, 2 with 3, 3 with 1. And the second is the single ion anisotropy of all the three spins. They are of the same form. Okay, we have a D tensor, and the D tensor is given by one parameter, namely theta. So that's the tilt of the easy axis away from Z direction. And then we of course need three oscillators. They are given by three frequencies. In the end, this will be the same. So we have got three oscillators, and the first oscillator is coupled to theta 1, and the second to theta 2, and the third to theta 3. And the third term is the Zeeman term. So how are they coupled to the anisotropy tensors? So this is the tensor. It's basically given by its easy axis, EI, with angles, polar angles, theta and phi. So this is a projector onto this easy axis with some strengths. And the angle is given by the angle without phonons plus a coupling to the phonons. Okay, so the mean we choose to be 0. So in the absence of phonons and also in the mean, the anisotropy tensors are uniaxial. So this is good. Okay, remember, this was bistability. This was a perfect SMM. Now, come on. Now we switch on the phonons, and we did an exact diagonalization, varying all the parameters. You know, there's this omega, there's the spin-phonon coupling. So you can play with these numbers, but the fundamental question always turns out in the same way. Phonons can induce a tunnel splitting. Okay, here you see a tunnel splitting as a function of B with phonons switched on, these three modes that can tilt the axis. But the interesting thing, result for us was that the ground state practically does not contain phonons. Nevertheless, tunneling occurs, so this gap opens. Nick Chilton and the Manchester guys, they termed this that the coupling to the 0-point motion of the oscillators is sufficient. So what's the bad news for us? The bad news is in this perturbation theory or scattering picture, one thinks that it's enough to cool down the system, okay? To die out or diminish the number of phonons. But this is not enough, yeah? It's not enough to cool down the system. The coupling to the oscillators or vibrations is sufficient to open a tunneling gap, okay? This has nothing to do with thermally decreasing the number of phonons. Okay, here's a side remark. Boris, it refers to you. I guess many of these things that we have rediscussed here are known in the field of vibronic couplings. Yeah, so if I spoke to Eugenio Coronado and Mikhail Atanasov, and they kind of agreed that the results are not surprising. So phonons can induce a tunneling gap. So in the last, say, 2 minutes, I speak about some, I would say, accidental discovery, namely when we look into phonons that couple only to the E term. So here, the next phonon I want to investigate is one where I have a single spin that has got a D tensor, and the D term, the easy axis term, I leave the same, and I only couple the E term, so this value, to vibrations, to oscillators. Yeah? Let's imagine such phonons exist. Are they interesting? That was our question. And the Hamiltonian is the same. So here is again the harmonic oscillator. So E is now coupled to the phonons, to the phonon mode, either in a linear way or in a quadratic way. And then something very funny happens, okay? Imagine we couple it in a linear way to the E term. Then for all, the spin is integer, I should say that. Then for even spins, say s equal 2 and 4, a tunneling gap opens, and for odd, it does not. Okay, this is not Kramer's degeneracy. The spin is always integer. Here it is 1 and 3, and here is 2 and 4. So this is an odd-even effect. It has to do that the E term couples linearly, in my assumption, to the phonon modes. If it couples quadratically, then the gap always opens. So one can generalize this. If the order of the coupling is odd, so could also be to the power 3 or so, then we have this behavior that odd integer spins don't have a gap and even do. And for the quadratic, we can generalize it to even powers, and then always a gap opens. Okay, this was more a funny investigation. The reason is a symmetry that is, you could mathematically describe as a supersymmetry. Of course, you would say, well, in a realistic scenario, then maybe the coupling would be like a Taylor series and contain all these odd and even powers. And then we would, of course, always see the opening of a gap. So with that, I'm finished. Let me summarize. We all know that magnetic molecules are interesting. That's why we are here. We know the challenges for single molecule magnets. I addressed phonons today and pointed out that phonons do not only induce transitions, but they also open a tunneling gap. I had the pleasure to work with many people in the field, and I'm thankful for that. And I thank you very much for your attention.
Yeah, thank you very much, Professor Schnack. So we are 74 now, so 74 participants are present, and I hope there are some questions to Professor Schnack. Please.
I will be happy to address them.
Yeah. Okay, so I can't see any yellow hand on the screen. So if I miss somebody who has a question, please turn microphone on and tell it. So because I see only
Boris Tsukerblat wants to ask a question.
Yes, I see.
Jurgen, this is very interesting phenomena you described. I have one question, maybe technical.
Yeah?
When you use phonons, you have quantum number of the phonons, and at a certain step of calculation, probably you need to substitute some equilibrium or some n plus 1. This is the first order or second order, or was the phonon quantum numbers?
Boris,
how you average?
Yeah, what we do is the following. So this is like exact diagonalization, okay? So what we do is we have here n1, n2, n3. These are the phonon numbers for the 3 modes that we have in the Hamiltonian, okay? And what we do is we truncate the Hilbert space. So
I understand this.
Say at n equal 5, for instance.
Yes, I understand. But at the end, you have this quantum number, n1, n2, n3. What are you doing with this quantum number of harmonic oscillators?
I don't do anything with that, because what I want is the spectrum, okay?
Is the spectrum.
Yeah,
okay.
Yeah. And what I find out is that the split ground state, basically does not contain phonons. So
yes, I understand. Now I understand. Thank you very much. It's absolutely interesting, absolutely nice. And thank you for your talk. Nice.
Thank you for your question.
Thank you.
Thank you for your question. So maybe further questions in the audience. So, but you can use chat also if you have questions. Please send your questions to Professor Schnack via chat. Yeah. Okay. Thank you. Thank you once again. And we move to another speaker. It's Eduard Feldman. Eduard, I have seen you. Yeah. Okay. Yeah. Please start your lecture.
Yeah. My presentation is here.
Yes, yes, we can see.
Yes. Yes, and a sound is sufficient.
Yeah, perfect.
Yeah. First of all, I would like to thank the organizing committee for my invitation to give a talk at the conference. It is a pleasure for me to tell you about quantum computer simulation of multiple quantum NMR dynamics of spin dimers. 40 years ago, Richard Feynman proposed harnessing quantum physics to build a more powerful kind of computer. Realizing Feynman's vision is one of the grand challenges facing 21st century science and technology. My talk can be considered as the first step towards an application of quantum computers to solve problems of magnetic resonance. What does it mean, quantum computer? Among numerous definitions, I choose the following. Quantum computer is a computational system which uses quantum superposition and entanglement for a transfer and processing different data. I suppose that concept superposition is well known for our audience, but I will tell a couple of words about entanglement in my talk. Quantum physics allowed us to realize quantum calculations, to investigate quantum networks, quantum teleportation, quantum metrology, quantum cryptography, and so on. We performed calculations on quantum computer on IBM superconducted quantum computer using long distance access. And I will demonstrate the IBM technique which was used in our calculations. Because entanglement is a main resource of quantum computer, I give a couple of words about entanglement as a measure of quantum correlations. We use multiple quantum NMR in our calculations, and I give a short introduction to multiple quantum NMR in solids. A special attention will be paid to multiple quantum NMR dynamics of spin dimers. We solved two different problems on quantum computer. First, we investigated multiple quantum NMR dynamics of dimer when the initial state of dimer was pure one. It is comparatively simple task, and I will discuss it in detail. The other problem corresponds to the same problem, but with the initial when the initial state is thermodynamic equilibrium one. The problem is that this thermodynamic equilibrium state, which is usual in practice of magnetic resonance, it is not a pure one, it is a mixed one. But it is well known that initial state for quantum calculations on quantum computer requires a pure state of the system. And we developed methods, so-called methods of purification, which change the 2-qubit mixed state on 4-qubit pure state. And I will discuss this method and obtain results. We performed our calculations on IBM quantum computations. This computer uses a Josephson effect and works at very low temperatures, approximately 15 millikelvins. Such temperatures are necessary in order to overcome the destructive processes caused by quantum decoherence. Here you can see a quantum processor which was used for solving our problem. It's too small quantum computer, but it is very important, and it is the same quantum processor in the increased scale. A long time people thought that quantum mechanics leads only to additional restrictions and is useful for development of quantum computation. However, it is not true. It was shown that entanglement is an important resource for a quantum computer. Entanglement is a measure of quantum correlation. If one has two independent states, the system consists of two independent states, which can be described by psi function psi and phi, then they are not, these states are not connected, and there are no any entanglement in the system, and there are no additional resource for quantum calculations. However, two states are closely connected in the superposition state, and then quantum correlations are very important for quantum correlations and quantum computation. It is worth to notice that such entanglement is significant only in very low temperatures. However, we showed in our works at the Institute of Problems of Chemical Physics that quantum correlations can be also not at sufficiently high temperatures when entanglement is absent, and so in some cases it is possible to realize quantum calculations at comparatively high temperatures. The states of a qubit can be written as 0 and 1, which correspond to spin 1/2 states up and 0. This state is the base of quantum calculations, and for two-spin system, which will be considered in my talk, we have 4 basis states: up, 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 down, down, up, down, down, and these two qubits can be in superposition state, which is given by psi function. There are a lot of different quantum operation, quantum gates. We will consider only 2 of them: one qubit operations, one qubit rotations. Here you can see the operator of rotation by angle theta about axis x, and we will consider 2 qubit operation, so-called control node or C node. C node is very important in quantum computing. It can be used to entangle and disentangle different quantum states. Moreover, according to Solovay-Kitaev theorem, any quantum circuit can be simulated to arbitrary degree of accuracy using a combination of C node operation and one qubit rotation. Thus, these gates form the basis of an arbitrary quantum algorithm, and our work is based on this theorem, and details will be further in my talk. We will use methods of multiple quantum NMR, and I give a short introduction to this method. It is a 2-dimensional experiment which consists of 4 different periods: preparation, evolution, mixing, and detection. During the preparation period, the system with dipole-dipole interactions is irradiated by spatial tailored multiple sequence. As a result, dipole-dipole interaction oscillates, and averaging these oscillations leads to emergence of multiple quantum NMR coherences, which are the main observables in this method. This coherence evolves on the evolution period. In order to obtain non-zero signals from different multiple quantum NMR coherences, it is necessary to use the mixing period. In this period, the system is irradiated again by multiple sequence, which is analogous to sequence which was used on the preparation period. However, phases of pulses are shifted to pi over 2. As a result, we obtain the same average Hamiltonian on this period, but with opposite sign. It is very important and is a basis for applications of multiple quantum NMR in different problems of physics, chemistry, quantum informatics, and it is possible to investigate quantum chaos with these methods and so on. But we will use multiple quantum NMR dynamics for investigation of dynamic dimer. The Hamiltonian of dimer is given here. It is only a two-spin system. Operators I1 plus, I2 plus are raising operators, and operators I1 minus, I2 minus are lowering operators. The scheme of multiple quantum NMR spectrum here is very simple. It consists of 3 different lines, which corresponds to multiple quantum NMR coherences of -2nd, 0, and +2nd orders. Consider the case when the system is prepared in pure ground state. This state is given here, 2 spin up, and it is a structure of multiple quantum NMR spectrum for this case. Existing theory allows us to obtain formula for evolution of multiple quantum NMR coherences. The results are given here, and the sum of multiple quantum NMR coherence is an integral of motion. The second case is thermodynamic equilibrium case. The structural spectrum is the same, but the theory gives more complex formula for intensities of multiple quantum NMR coherences. Evolution of multiple quantum NMR coherence is determined not only time of evolution, but also the inverse temperature in the system. Here below you can see the sum of coherence as an integral of motion. Now I would like to tell you about our simulations of spin dimer dynamic on quantum computer. We will consider the case when the initial state of the system is pure 1. We have 2 spin systems, 1 and 2. These spins are in states up. It is a pure state. And first, we apply the 1 qubit rotation around above axis x, and as a result, instead of initial 0 state, we obtain a superposition states of states up and down. After this operation, we apply the control node, where first spin is control 1 and second spin is touched. It means that the flips of second spin takes place only if the first spin is in state down. As a result, we change the obtained earlier superposition state and obtain superposition state consisting of state 0, 0 and 1, 1. Up, up and down, down. It is very important because existing theory shows that namely these states are responsible for multiple quantum NMR coherences and gives the intensities of multiple quantum NMR coherences. It is necessary to obtain probabilities of these states. It is significant that these probabilities were obtained on quantum computer with operations of measurement. According to existing theory, intensities of multiple quantum NMR coherence are determined by these probabilities, and we can compare results which gives the existing theory. Evolution of this theoretical curves are given by solid lines, and points were obtained through calculations on quantum computer. You can see that we have very good coincidence of these results, but small discrepancy is connected with error of control node operation, which was used in this calculations. Now I would like to consider the second case, when the initial state of the system was thermodynamic equilibrium 1. The point is that this state isn't pure 1, it is a mixed state. Really, rho squared isn't equal rho for this state. However, we showed that if we add one additional spin to this thermodynamic equilibrium spin, we obtain pure two-spin system. Let we represent this state through such expression, which depends on parameter theta, will be determined below. Using the psi function psi sub 2, we can obtain projector operator, and tracing this projector over the additional spin, we obtain diagonal matrix for one spin. If parameter theta is connected with inverse temperature of the system with this relationship, then we obtain thermodynamic equilibrium state. It means that we use this projector for calculations which contain all information about thermodynamic equilibrium state. Because we have 2 qubits, we should repeat these operations over the second spin of dimer. The purification of 2 qubit states yields the pure state of the 4 qubit system. This 4 qubit system is given here. It is necessary to obtain this psi function on quantum computer. The initial state of quantum qubits for quantum qubits are 4 up spins. First spin up, second spin up, third spin up, and fourth spin up. 4 spins of quantum register of quantum computer. However, using control node operations and 1 qubit rotation, we can obtain from this simple pure state another pure state which is equal to this state. In order to investigate evolution of this state, it is necessary to calculate evolution of our psi function. Evolution is determined by evolution operator, where H23 is Hamiltonian of dimer, consisting of spin 2 and 3. And according to theorem Salovey-Kitaev theorem, this operator can be obtained with C0 operations and 1-qubit rotations. However, it requires some mathematical skills to realize this theorem, and we realize it, and the corresponding results is represented here. Below, you can see the quantum scheme of all calculations of multiple quantum NMR dynamics of spin dimer prepared in thermodynamic equilibrium state. This scheme gives right initial state, and it realizes the quantum calculations with this operator, evolution operator. As a result, we obtain on quantum computer psi function, which can be calculated analytically also. It is here, and it means that we can obtain a projector, and tracing this projector over additional spins 1 and 4, we obtain the density matrix of spin third and second and third. We obtain dimer density matrix. The probability, the diagonal elements of this matrix are the probabilities of states up, 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 down, down, up, down, down. And knowing of this operator is very important in order to obtain intensities of multiple quantum NMR coherences. These intensities, according to existing theory, are connected with probabilities of multiple quantum states, and these probabilities were obtained on quantum computer, and using these equations we can compare the theoretical evolution of multiple quantum NMR coherence of the zeros and second order, and results obtained on quantum computer. You can see that we have a good agreement of these results, but discrepancies between theoretical and simulated on quantum computer results isn't coincide completely. The point is that we used a lot of control knot operations, and so the errors of these calculations are sufficiently large. It is the main problem of quantum computations now. The main conclusions of my talk can be presented as follows. The spin dimer dynamics was investigated on a 5-qubit platform of IBM superconducting quantum computer. Intensities of multiple quantum NMR coherences calculated on the quantum computer are in a good agreement with theoretical predictions. The purification methods for creating the mixed state on the quantum computer was worked out. Here you can see laboratory of spin dynamics and spin computing of the Institute of Problems of Chemical Physics in Chernogolovka. Our laboratory was one of the first in Russia dealing with problems of quantum calculations. We continue our work in this direction. And in conclusion, thank you all of you for attention.
Yeah, thank you, Professor Feldman. Thank you very much. So my question to the audience, who has a question? Who would like to ask? Professor Fedin, please.
Thank you very much, Eduard Benjaminovich. Very interesting. Maybe completely irrelevant question. Do I understand correctly that all these multi-quantum coherences, actually multi-quantum transitions, are partly forbidden. Does it make potential problem for implementation so that spin manipulation will be a little bit slow? I mean, slower than manipulating spins via allowed transitions.
Maybe I don't understand you, but it seems for me that the velocity of simulation doesn't depend for our simulation process. The problem is how to calculate on quantum computer not 2 spin system, but for example 4 spin system. It is a problem today because it requires we have such algorithm, but errors of such algorithm will be very large.
But if transition is weakly allowed, then the rotation of spin at a given applied radio frequency field will be quite slow. That was my question, basically. Or maybe this is not relevant. I don't know.
No, it is not relevant because these rotations are not rotation with physical process. It is formal gates, formal quantum gates for quantum algorithm. It is not connected with details of quantum states.
Yeah. Okay. Thank you.
Further questions? I don't see any questions. And we thank again Professor Feldman for his presentation, for his lecture. And we move to another speaker who represents International Tomography Center in Novosibirsk, Irina Golomolzina. Irina?
Сейчас я сейчас. Так, остановить. Так, вроде бы справился.
Эдуард Бениаминович, отключите, пожалуйста, микрофон.
Да.
Hello. Can you hear me?
Sure.
Yes, we can hear, but we need your presentation. Please open your presentation. Yeah. Can you make it full screen? Yeah, thank you.
Good morning, dear colleagues. In this presentation, I would like to tell about my work devoted to the intricate transformation of heterospin complexes. In our, the main areas in our laboratory is devoted to study of unique class of object of multi-spin coordination compounds. So they call it Brisson crystals. They're based on polymer chain complexes of hexafluoroethylacetonate kappa and nitronil nitroxides and trietbutyl nitronate nitroxides radicals. This classes compounds is characterized by phase transition with anomalous displacement of paramagnetic centers in crystals. This displacement causes a mechanical response, here huge change in volume in the unit cells of the crystals at the temperature change. Rearrangement are always accompanied by changes in color and magnetic properties. You can see the color change of the samples which appeared with liquid nitrogen on video. When studying the effect of the Brisson crystals, we unpredictable results were obtained. In the first, it was shown that the introduction, the third position in the pyrazole cycle alkyl substituent, we were obtained the first example of a reversible single-to-single crystals polymerization depolymerization accompanied by a magnetic anomaly for transition metal complexes and stable radicals by variation of temperature has been demonstrated. The choice of imidazoline ring as paramagnetic ligand was dictated by the fact that the usual arrangement on the nitroxyl radicals fragment and the imine nitrogen atom is in its molecules was topologically similar to arrangement pyrazole ring, pyrazole nitroxyl, pyrazole nitroxyl nitroxide studied earlier. However, chemomechanical activity was found. This effect is evident at complexes of metal transition hexafluoroacetylacetonase with methyl imidazolyl substitute nitroxyl nitroxides. Under ambient conditions, the jumping and various displacement of crystals lasted for several weeks. As a result, coordination ligand were restored with the release of atomic oxygen followed by the rupture of the crystals. So nitroxide can spontaneously lose oxygen and there is transformation into corresponding immunonitroxide. Surprising effect was found on polymer chain complexes with ethyl imidazolyl substitute nitroxyl nitroxide with hexafluoroacetylacetonate copper. It was shown that polymer chain alpha complex, the first colon, lead to a degree of a magnetic moment. However, it is not a spin transition in the statin alpha complex, but rather the consequence in the irreversible space transformation of alpha into beta complexes induced by cooling of the metastable alpha modification. When the cooling and heating cycles repeat further, the reversible spin transition in beta complexes is reproduced. The next step of the study was retrace the effect of moving nitroxyl nitroxides label in the pyrazole cycle in the first position to the fifth position, and it was found that the change of position led to a significant decrease in the plasticity and suppression of the breathing crystals effect, and only one binuclear complexes has a spin transition. The question of replacing of nitronyl label with the tributyl label at the fifth position of pyrazole cycle remained open. The uniqueness this group of compounds is that we approach the paramagnetic senses closer to the donor nitrogen atom. In this presentation, I'll tell you more about my synthetic radicals and also speak about the complexes obtained with them. It's the synthetic scheme is shown on the slide. To obtain paramagnetic ligand, we use the standard organic reaction. The first step in alkylation of pyrazole. Then the reaction of an alkyl pyrazole with n-butyl lithiums, which give the corresponding lithium derivatives, which were reacted with 2-methyl 2-nitrosopropan. the obtained hydroxylamine were confirmed by X-ray, and the product was synthesized by oxygen of hydroxylamines with potassium hexacyanoferrate in presence of sodium bicarbonate. I would like to note that the certain difficulty appears during the oxidation. It turned out to be a difficult scientific task to obtain a radical without impurities. The major problem was easy oxidative transformation of nitroxides. The oxidant potassium hexacyanoferrate is very weak. However, other product was obtained in the mixture with hydroxylamine or a radical and on corresponding pyrazole trade butyl neutron were given. Only reaction with kappa hexafluoroacetylacetonate, the structure of neutron were confirmed by X-ray. Experimentally, it was possible to pick up the ratio for oxidation, and the reaction time increased the alkyl group increases. To freshly prepared radicals were red oils. Radicals were taken at the rate of 85% yield to obtain the complexes. In the interaction of resulting nitroxide with kappa hexafluoroacetylacetonates, we were given a number of complexes with molecular and polymer chain structure. So in the solid phase, the crystals of mononuclear complex, binuclear, and the crystals of polymer chain complexes were obtained. This slide was show examples of structure of the complexes. Let us consider in detail the complexes with the methyl substituent. The reaction the kappa bis-hexafluoroacetylcetonate with methyl ligand in heptane at the temperature minus 19 degrees, we obtained mononuclear complexes. This structure was confirmed by X-ray. This is centrosymmetric complexes, and the paramagnetic ligand are coordinated by nitrogen atom pyrazole cycle, and the distance kappa of kappa nitrogen is 200.060 angstrom, and distance kappa oxygen is 1.986 and 2.250 angstroms. The molecular packing in such that short contacts are formed between uncoordinated NO groups. The bond distance between nitrogen-oxygen is 2.307 angstrom, and oxygen-oxygen is 2.612 angstrom. Because of the short distance between them, the chains of molecules in the structure can be isolated. Such contacts reason a value magnetic moment which remains constant over time. In entropy and temperature range is actually determined only by the spin of the copper ion. The brown crystals of the complex with a polymer chain structure with head-to-head motif are readily isolated with a higher yield from the hexane solution of the equivalent amounts metal and ligand. In the result from bridging coordination ligand with the central symmetric coordination of the copper atom in the matrix completed to octahedral by atom nitrogen of a pyrazole cycle or oxygen oxygen of the nitroxide groups. The bond length is shown on this slide. When the temperature increases, the bonds are short by less 0 to 0.06 angstrom. The value at the temperature is 2.7 Wolf magneton. With further decrease in temperature, value increases reaching and maximum value of 3.1 magneton Bohr at 5 Kelvin that are characteristic by ferromagnetic exchange. The reaction copper hexafluoroethylacetanates with ethyl radicals gives a polymer chain and two structure binuclear complexes. I will tell dimer 1 and dimer 2. The dimer 1 was obtained in the hexane at the temperature minus 18 degrees Celsius. Yield is 56%. Dimer 2 was given in heptane. Yield is 65%. It is interesting that the molecule geometries are simulating, but they have different packaging. The polymer complexes was obtained at the temperature 55 degrees using the 3D solvent. The crystals fall out immediately. The color of crystals is light orange, which gradually change a dark green. Such a sharp and rapid color change motivated us to study in process in detail. It was shown that the temperature 275 Kelvin, the polymer complexes undergoes an irreversible phase transition into the dimer 2. A detailed description of the transformation will be reported in the next presentation, Professor Romanenko. Two modifications of binuclear complexes, dimer 1, dimer 2, and polymer chain complex were obtained with propyl ligand. It was particularly difficult to get the phase data in pure form. Much research have been done, choosing an optimal condition. The dimer 1 was obtained in fresh distillate hexane with minimum humidity at the temperature minus 18 Celsius degrees. Yield is 43%, and it cannot be left at the room temperature. The dimer 2 we were not able to select in scientific systems, but it was isolated mechanically from the mixture with the polymer chain complexes. The difficulty is that the chain has a dichroism from orange to dark green, the dimer 2 dark green. The polymer complex is isolated when octane containing metal and radicals in ratio 1:1 while heating. The yield is 65%. In addition, the chain was obtained is other solvent, nonane and decene, with yields 85 and 90% respectively. It was found that initial temperature and the way of adding the radical solution to the metal solution are important for the reaction. The radical solution must be added in portion to obtain a pure chain. Otherwise, you get a mixture with dimer. It was shown that when temperature is 295 Kelvin, the dimer 1 undergoes reversible phase transition to dimer 2, with the crystal well cracked. The dimer 2 is transformed into the dimer 1 at the temperature 240 Kelvin. It would seem that we have observed similar transformation many times on other copper nitroxyl systems, but it is a different case. Phase transition from dimer to chain complex when heated to 303 Kelvin. The dimer arrangement into a chain with preservation of paramagnetic centers. We found only one example in the literature. This is transition and irreversible. However, we decided to heat up our polymer chain complexes a little bit more. It was found that when heated to 320 Kelvin, the polymer complex, the intricate transformation into the new complex. According to preliminary X-ray data, it was found that a new pyrazolone ligand is formed. The pyrazolone is coordinated oxygen and nitrogen atoms of the pyrazolone fragment. The new ligand is diamagnetic. The video shows a process of transition from dimer to the chain complexes. X-ray and magnetochemical studies were carried out to confirm our hypothesis, about which Professor Romanenko will speak in detail in the next presentation. To sum up, I would like to present our result. We succeed in synthesizing a new group radicals and complexes them of various structure. For the first time for complexes with new radical and kappa HFAC, the phase transition are demonstrated. It was revealed that the polymer chain complex undergoes an irreversible phase transition into complex binuclear complex. It was found that when temperature rises, dimer 1 undergoes a reversible phase transition to dimer 2, which occurs an irreversible phase transition to thermodynamically more stable polymer chain complexes. It was shown when heated, the polymer chain complexes experience the sophisticated transformation into the complex, a new complex, through rate a new diamagnetic pyrazone ligand is formed. I would like to thank my dear colleagues and thank you for your attention.
Yeah, thank you, Irina. Please, questions to Irina. Yeah, Sergey Weber. He has question and he thank you also.
Thank you very much for the presentation. You showed several examples when you change slightly parameters of synthesis, such as solvents or temperature, and it results in a new product. But could it also be that for the same conditions, the same solvent and the same temperature, you will get different structures at once, so in the same time? And what do you do in these cases? How do you try to understand at which conditions each of these phases could be obtained? Thank you.
Thank you for a question. This is my work. Sorry.
Okay, I can actually ask it during the coffee break if you
Yes.
like. Thank you very much.
Sorry.
So you can send your question in chat to Irina. So any other questions? No, I don't see any questions. So thank you, Irina, again for your nice work for presenting it. And we move to another speaker, Professor Galina Vladislavna Romanenko. Yeah, exactly. Galina Vladislavna Romanenko. She comes also from International Tomography Center. Irina Vladislavna, Professor Romanenko, yeah, I see you. Please show us your presentation.
Yes. Так.
Yeah.
Yes, can you see my presentation?
Yes. Everything okay. Yes.
Okay, thank you, Mr. Chairman. Good afternoon, dear colleagues. First of all, I would like to thank the organizing committee for giving me the opportunity to share the result of our research at this conference. This report is continuation of previous one, in which Irina Golomolzina talked about the synthetic side of research and showed short film about intersections of crystal. I want immediately draw your attention to the fact that with the increase in the size of substituent, the number of formed complexes increases, and it is difficult to imagine how many of them can be isolated for the ligand with butyl substituted nitroxide. So there are only two complexes of copper hexacetoacetylacetonate with methyl nitroxide. As they told us, this is one of them is a mononuclear complex with very short distance between nitroxide group of radicals of neighboring molecules. And the second is the chain polymer complex with head-to-head motif of polymer chain. In this chain, as you can see, single copper ions in these coordination units alternate with copper ions in coordination units copper over 6 that is same spin exchange clusters. Copper oxygen distances in them define the character of exchange interaction and magnetic properties of complexes. As you can see, for this complex, copper oxygen distance is about 2.4 angstroms and barely change upon cooling up to 100 Kelvin. This distance corresponds to ferromagnetic exchange interaction in the spin exchange clusters. As studies of the magnetic properties of this complex have shown, upon cooling the sample of this complex from room to helium temperature, the value of effective magnetic moment increases. For ethyl substituted nitroxide, the chain polymer complex of the same structure was obtained, and it has a similar temperature dependence of the effective magnetic moment upon cooling the sample from room temperature to helium temperature. The only difference between these two complexes is that the complex with ethyl nitroxide is formed by two crystallographically independent chains, and the distances in them are somewhat larger than in the complex with methyl nitroxide. In addition, two polymorphic modifications of binuclear complex were identified. The molecules are very similar, and the main difference between these molecules is in nitrogen distances and the inflection of acetylacetanide ligand along oxygen line. In the end, these differences lead to a difference in the pattern of molecules. I'd like to note that both modifications are diamagnetic. Oxygen distances into spin exchange clusters are less than 2 angstroms. Our visual observation showed that if we leave the sample of chain polymer complex at room temperature for some time, its color changes from light orange to dark green. As shown by X-ray diffraction study of this sample, the obtained compound is the second polymorphic modification of the nuclear complex with this ligand. This was also confirmed by the result of magnetic chemical experiments. I have already said that when the sample of the chain polymer complex is cooled, the magnitude of effective movement increases. But if we start to heat the sample, the value of the effective movement gradually decreases to the initial value at room temperature, and but the time variation of magnetic properties of sample that was left in discrete magnetometer at 300 Kelvin showed that within 3 hours the value of mu decreases from 2.7 boron magneton to half of boron magneton. That is, the sample becomes practically diamagnetic. And further cooling of this sample led to further decreasing in mu. It should be noted that the solid phase transition of polymer into dimer is non-trivial not only for complexes with nitroxide. We found the only literature example of similar transformation, but in that case, conversation process accompanied by solvent exchange in crystalline state. In addition, I would like to note that in the process of synthesis and optimization of conditions for obtaining monophase samples, the ethyl substituted nitroxide can transform into ethylpiazolone an oxide. This ketone also can form the polymer chain complex, but copper coordinate not an oxide oxygen, but piazolone oxygen. I have already noted that about the diversity of complexes with increasing in the size of substituent. And for papyl substituted nitroxide, we were lucky to isolate this such a group of complexes. First of all, there was two polymorphic modification of binuclear complex and two polymorphic modification of the nuclear complex, and also two polymorphic polymer chain complexes with modification with started nitroxide and transformed piazolone and oxide. This complex is a structural complex with the seal substitute nitroxide, just I described. And the most interesting thing for this for complexes with this nitroxide is that solid phase transformation that we observe is different from those for complex with acyl nitroxide. Moreover, they are much more sophisticated. We were very lucky that we were able to follow up all this process, not only by method of magnetochemistry, but also to trace this transformation single crystal using X-ray diffraction method. In the first stage, we found that the reversible power transformation of between two polymorphic modification of the nuclear complex. And Dimer 1 is more stable below minus 10 degrees centigrade, but if Dimer 2 is stable at room temperature. Because this process is reversible, we understand that in our further experiments we can use the crystal of Dimer 2. And I'd like to note that these both polymorphic modifications are diamagnetic, as in complex with acyl substituted nitroxide. In this slide, we can see the data of structural transformation of Dimer 2 single crystal obtained by us during X-ray diffraction experiment. The crystal of Dimer 2 was fixed on a glass rod and covered with fast-acting glue at temperature about 290 Kelvin. Then we installed it on diffractometer, checked the unit cell parameters, and made sure that this is a single crystal of Dimer 2. Then we raised the temperature to 300 Kelvin and started the matrix experiment and found that in crystal the presence two domain in our crystal, the main domain is Dimer 2, and the second chain polymer complex. But the reflection of this domain was 10 times bigger than the reflection of main domain. Then the temperature was increased to 303 Kelvin, and we started full diffraction experiment. At first 5 runs, a reflection of domain of polymer complex became stronger, but the reflection from Dimer domain weaker and finally disappeared at all. But the quality of crystal became worse. And to run number 7, all reflection have practically disappeared. But an hour later, after that, we were surprised to see the improvement of diffraction picture, and diffraction picture then became more good, and we understand that this is a diffraction picture of single crystal. After finishing the experiment, all around starting number 8, we integrate and determination of structure showed that this is a chain polymer in which instead of papyl substituted nitroxide, we have in the function of bridging ligand papyl pyrazolone amine. It was very unusual for us, very surprising. Next slide provides a summary of conversion of Dimer 1 to complex with chain polymer complex with papyl nitroxide and the chain polymer complex with papyl pyrazolone amine. I should like to note that upon transformation from binuclear to chain polymer complex, copper oxygen distances in exchange clusters changes and it should lead to a change in the nature of exchange interaction in exchange clusters. And subsequent, and after that, and it was confirmed in the observed and magnetochemical experiments. At this slide, you can see the change of value of the effective magnetic moment for dimer 1 with increasing temperature from helium to room temperature. And you can see that, as you remember, dimer complex are diamagnetic, and the mu value up to 300 Kelvin is very too low, but at 305 Kelvin, mu value sharply increases to 3.9 Bohr magneton, and upon subsequent cooling goes to 3.2 Bohr magneton at 25 Kelvin. That corresponds the polymer chain complex with nitroxide, and consequently the presence of ferromagnetically coupled spin in the exchange clusters and the weakly interaction with them, single copper-ions from these coordination units. With that, with subsequent cooling or heating of the sample, the mu value come back to the value of at 300 Kelvin, 300 Kelvin, and if we left the sample in the magnetometer, we can observe the decreasing in mu from 3.9 Bohr magneton to 2.6 Bohr magneton, which corresponds to the presence in the complex only 2 interaction spin of 2 copper ions. And with subsequent cooling, this value does not change practically. Thus, recorded structural transformations of complexes are fully confirmed by the data of magnetic measurements. Summarized all the data, I would like to note that we found 2 examples of mutual conversation of copper nitroxide complexes recorded by single crystal X-ray diffraction and magnetometry from chain complex to molecular binuclear complex for acyl substituted nitroxide, and from chain polymer complex or binuclear complex to chain polymer complex with nitroxide, and further to polymer complex with transformed ligand. And finally, I would like to, on my behavior, on the behavior of my colleagues, to thank you, all of us who listening to this report. Thank you.
Yeah, thank you very much, Professor Romanenko. So we have some time for questions or comments, maybe. We are a little bit out of time, so we are a couple of minutes out of schedule, but 1 or 2 short questions we can ask. Please. Yeah, Professor Bubnov.
Galina Vladislavovna, thank you very much for your intriguing presentation. I have one question. Why normal propyl group provides so interesting properties?
It's a very interesting question because previously we observed very interesting effects with nitroxide, with ethyl substituted the nitroxide radicals. it was attention of this group during the phase transitions, but for propyl substituted nitroxide, we observed this process for the first time. I can't say what we can see in other experiments with other substituted nitroxides.
Thank you.
Yeah.
Thank you very much.
Okay, thank you. So on behalf of all the participants of this session, I would like to thank again all the speakers of this session for very interesting and very nice presentations of chemistry they have done. And before we finish this session, I would like to give a chance to make a short note to Professor Fedin. So he asked me to give him a chance to say something.
Yeah, thank you very much. Galina Vladislavovna, would you please close your presentation?
Yes, I'd like to, yes.
Yeah, just do it like this. So I have a very short announcement. I'd like to say that the option to view posters online is already active. I just try to see how to demonstrate that. It's strange. I do not see the option for that. I just want to show you how it works. Yes, exactly. So it's just here on the screen. You have our website. You see the conference. You see the program. Then this is the program at a glance. And just below that, you can see links to the posters. 3 posters have been sent to us. So those who wish to look at posters in advance can use this option like this. That's it. And otherwise, also we invite those who wish to send their posters in advance to our conference website. That's it. Thank you.
Okay, thank you, Professor Fedin. So, dear colleagues, the next session will start at 3 p.m. So we have 20 minutes break till the next session. Okay, see you. Thank you.
Добрый день, Сергей.
Good evening, dear colleagues. My name is Vyacheslav Kuropatov. I am from Razuvaev's Institute of Organometallic Chemistry from Nizhny Novgorod. Professor Fedushkin was not able to attend at today's last session and asked organizers asked me to be a chairperson. Maybe you just seen translation from a web camera. This web camera is on the hotel, which might be a lobby for our conference. It is a pity that was not possible to hold conference in person in Nizhny Novgorod. The city has become even better and more beautiful before 800th anniversary. The weather is also favorable, but coronavirus crossed everything out. I hope that maybe it will be possible to meet in Nizhny Novgorod some other time. This session first presentation will be done by Konstantin Zvezdin from Prokhorov Institute of General Physics from Moscow. Konstantin.
Do you hear me? My name is Dmitry Plokhov. I will replace Konstantin Zvezdin for this report. I am also an author of the report.
Okay.
Let's start my presentation. Do you see my presentation?
Yes.
Let's full screen regime. Let's start. In recent year, considerable attention has been paid to the study of fine magnetic particles. Fine particles are understood as systems with sizes from units to hundreds of nanometers in at least in one dimension. Fine particles possess remarkable properties that solids, of which they are part themselves, do not have. The materials that make up fine magnetic particles are very diverse, from completely conventional materials to unusual materials in terms of magnetism. Fine magnetic particles are attractive for a wide variety of fields and applications. The most interesting for physics is the development of quantum technologies. We should note, that the development of quantum technologies does not necessarily mean getting into a race to build a quantum computer. The quantum properties of fine magnetic particles are interested in themselves. We can also say that they are somewhat nutrient medium for revealing new quantum coherence effects. The magnetic tunnel junctions is a basic element of modern spintronics. The discovery of a magnetic resistance effect enabled a huge industry based on the storage and processing of big data. The use of a magnetic tunnel junction allowed to increase the information density in modern hard drives by more than 1 billion times compared to the first models that appeared on the market in the middle of the last century. Although the specific stack design, layer composition, and geometry of magnetic tunnel junction is developed based on the required characteristic of the device, this structure can be quite complicated, as you see. But the main physical effects associated with the dynamics of magnetization are concentrated in so-called free magnetic layer. In modern spintronic devices, the dimensions of this layer are approximately 10,000 square nanometers, but thickness is about 1 nanometer. So the free magnetic layer of the magnetic tunnel junction is a typical fine magnetic particle. The trend towards miniaturization of the technological process will inevitably make the free magnetic layer to be a quantum device. Modern spintronic is based on a combination of two key effects. The first effect is a tunnel magnetoresistance, which makes it possible to electrically detect the state and dynamics of magnetization. Magnetoresistance ratio typically reaches 100 or 200% in industrially fabricated MTGs and may reach 5 or several more 100% in the best sample fabricated in advanced laboratories. The second effect is a spin transfer. Electrons which pass through the fixed magnetic layer get spin polarized, and when they are consequently injected into a free layer, they transfer their spin to the local magnetic system, creating torque, which acts on magnetization. Spin transfer torque induces dynamics is described by modified Landau-Lifshitz-Gilbert equation, which additional terms responsible of spin transfer effects. The combination of magnetoresistance and spin transfer effect forms the basis of a whole family of spintronic devices, in which the magnetic tunnel junction is the main basic unit. The design of each device is optimized for the operation of a particular device. Let us consider in more detail the main effects associated with the magnetization of a free layer. The first effect is a binary switching of the state of a magnetic tunnel junction. The device is designed in such a way that the energy of a magnetic system has two local minima, and the spin current can reversibly switch the magnetization from one minimum to another, and vice versa. Magnetic random access memory is based on this effect, and we will see below that there is an analog on this effect also in quantum dynamics. The second effect is the emission of a microwave radiation by a magnetic tunnel contact under the action of a spin current. In this case, the stack is designed in such a way that only one energy minimum remains in the system. And under the action of the spin current, the magnetization begins to oscillate around the equilibrium position, and consequently the resistance of the device also oscillates, creating a microwave signal. There is also an interesting inverse effect of microwave rectification. In this case, the microwave spin polarized current induces magnetization oscillations. The microwave current component is multiplied by the corresponding resulting microwave resistance component, creating a direct current component in the output signal. Supersensitive microwave detectors are created on the basis of this effect, with noise equivalent to the power parameter close to the current limit. In our laboratory, active experimental studies of this effect are underway. Ultra-wide band passive rectification of ultra-low power microwave signal down to several nanowatts was discovered. A very promising idea of spintronic is a spin orbitronics. In this case, chargeless pure spin currents are used to control the magnetization of free layer, magnetic fine particles. For this, a small magnetic element is deposited to a layer of materials with a giant spin-orbit coupling. Due to the spin Hall and Rashba effects, when an electric current is passed through this material, a spin current is generated in perpendicular direction to the electric current. Getting into a magnetic material, the spin current creates a torque with the help of which the magnetization is controlled. The table shows the spin Hall angles of various materials. This angle characterizes the efficiency of converting an electric current into a spin current. For heavy metals, it is less than unity. But for quantum materials, such as topological insulators, it can reach several tens. As mentioned above, Spintronics is rapidly moving into the quantum realm. The process of producing spintronic structures with a characteristical size of 22 nanometers has already been industrially mastered. Next year, a transition to the 16 nanometers standard is expected, and the rate of reduction of the feature size in technical process is predicted to be higher than the one in semiconductors. Thus, it can be expected that the production of quantum spintronic devices will become possible in a few years. Next, we will discuss what the main quantum effects can be expected in this area. These quantum properties we will view at an unusual angle in comparison with the properties of superconducting tunnel junction, since these at first glance different systems actually have much in common. This is important since the size of magnetic show stable size elements of spintronics in our
We can't hear you.
The dynamics of Josephson junction is the dynamics of parameters.
It's look like microphone of Dmitry don't work right now.
Something happened. We can't hear any.
Dmitry, sorry, please try to speak loudly because something was happened just 1 minute back.
Yeah, it seems your microphone is now kind of turned away or something like this.
Yes.
No, we still cannot hear you.
Hello, hello. Hello, do you hear me?
Not really. It seems that your mic is switched off. Maybe you need to just try to switch it again. I mean, physically.
Switch on.
Теперь да.
Nothing else? О, отлично. Так, теперь надо я.
Совсем пропал. А, нет, есть.
Алло, алло.
There is still a problem. Все равно проблема.
Непонятно, с чем связано. Я вас хорошо слышу, очень хорошо. Почему меня не слышно?
Микрофон из гнезда, может, выпал какой?
Нет, нет, я с ноутбука, как сначала, все шло, ничего не менялось.
Ну вот сейчас лучше стало.
Сейчас хорошо слышно, попробуйте.
Давайте попробуем дальше. Single Josephson junctions. You can see the figure of the single Josephson contact. And the dynamics of the contact is the dynamics of this other parameter. The equation motions is formulated on Lagrangian formalism, and transition to quantum description is made by Anderson approach. Generalized coordinate and generalized momentum are supposed to be operators. Such a system can also be considered as some kind of artificial atom, in the sense that by changing the parameters of a junction, we can change its properties at our discretion. To add, the local minima in potential energy can be used to construct a qubit on this base. The dynamics of magnetic moment of small nanoparticles driven by spin polarized current is formulated on the basis of modifying Landau-Lifshitz equations, which can arrive to this Lagrangian that has the same form as the Lagrangian for quantum dynamics in small Josephson junctions. With this isomorphism suggests that there are also similar quantum microscopic effects in the dynamics of this system. For the manifestation of quantum effects, we need to assume that the damping is weak. We will not discuss the details of the solution. We will only indicate the main results. The spectrum of the system is band one, like electron bands in a crystal. The wave function are block function specified by a continuous parameter called the quasi-spin. The corresponding excitations, quasi-particles with a fractional spin number, are very close in their properties to anionic excitation. The spin current excites coherent quantum oscillations of the precession motion of the magnetic moment. Thus, a wave packet, which at the initial moment of time has a zero average value of quasi-spin, shifts to a boundary of a brilliant zone, reflects from in, propagates to another boundary, again reflects, and so on. This process is called Bloch oscillations. Each reflection from the brilliant zone boundary appears as a jump in magnetization. As the spin current increases, the general tunneling effects arises between adjacent allowed bands, which results in hysteresis behavior of magnetization. Now we should note that in order to observe the considered effects in ferromagnetic small particles, quite stringent requirements are imposed in terms of its size. They should be approximately an order smaller than the size of Josephson junctions. This requirement can be weakened by the use of antiferromagnetic materials, but in any case, modern technologies for the manufacture of multilayer elements are only approaching such dimensions. There is another problem, and is also characteristic for superconducting elements. Artificially produced magnetic particles will certainly have some undesired distributions of characteristics. In this aspect, we propose to pay attention to new materials based on single molecule magnets, which can be devoid of indicated disadvantages. But we won't focus to one very interesting class of single molecule magnets, molecule with toroidal ordering. They are called in literature single molecule toroids. The toroidal moment appears in electrodynamics when solving the problem of finding the time average magnetic field with a stationary distribution of electric currents. Here we can see definitions in case for distributed electric currents and for localized spin and magnetic moments. The concept of toroidal moment dates back to the works of Shubnikov and Zeldovich. The existence of a toroidal moment in electrodynamics was shown in Dubna by the group of Cheshkov and Dubovik, and was experimentally discovered in cesium nuclei, and shortly after that, the existence of toroidal ordering of spin moments in solid-state physics was also demonstrated in Russia. The important features of the toroidal moment are, first, the toroidal moment is conjugate to an electric current or crossed electric and magnetic fields. And toroidal ordering of the physical system is accompanied by the possibility of observing a linear magnetoelectric effects in it. This provides a very powerful tool to control spin states by purely electrical means. To study the influence of the above factors on the toroidal moment of single molecule toroids, we consider the progenitor of the whole family of such molecules, the molecular cluster dysprosium 3. It is necessary to obtain a spin electric Hamiltonian, which was done by our research group for this kind of molecules. What about quantum dynamics? If we consider non-Kramers base array of ions of the Ising type, the ground state is non-degenerate. It consists of two closely spaced levels and can be considered as a qubit. The problematic is important in relation to quantum computing. How to control the states of a qubit, how to perform logical gates, and so on. A quasi-doublet state is featured by the phenomenon of microscopic quantum tunneling of the toroidal moment through the barrier separating two states with close energies. This phenomenon is similar to the well-known microscopic quantum tunneling of magnetization. And the problem, of course, can be solved using the similar already discussed technique based on Lagrangian formalism. The electric current, due to the coupling with the toroidal moment, can also lead to a reorientation of the toroidal moment. This effect can be considered in the framework of the Landau-Zinner approach. Due to Zinner tunneling, the effect of hysteresis behavior of the toroidal moment is also possible. On the left figure, we can see the probability transitions between states that differ in the sign of the projection of the toroidal moment. These Rabi-type oscillations arise due to the microscopic quantum tunneling of the toroidal moment. On the right figure, we can see the change in the projection of toroidal moment caused by the flow of electric current through the molecules. To conclude, we should again stress that modern spintronic gradually decreases to the quantum regime, and we should pay considerable and particular attention to the quantum properties of basic elements of spintronics. Thank you for your attention. That's all.
Thank you, Dmitry. The talk is open for discussion. Valentin, please.
Yeah, thank you for a nice presentation. I'm trying to envision a device in which you can somehow embed this single molecule toroids or other molecular magnets to be able to measure whatever you measure in, say, transfer. So is it, again, layered structure with some layer substituted by molecular magnets, or is it another kind of device?
We believe that it's some kind of substitution. The very, we think, difficult problem to handle with single molecule magnets is their sensitivity to magnetic noise, to stationary magnetic fields. The novel degree of freedom, toroidal moment, is devoid of this drawback and can be quite nice substitution. But the problematic can need further research.
Any more questions? No. We move to next presentation. And it's my pleasure to introduce Nikolay Efimov from Kurnakov Institute of General and Inorganic Chemistry. Nikolay, please, your presentation. microphone switch on.
Yeah, I see. Right now it's look like you can hear me. Thank you, Vyacheslav, for your kind introduction, and thank all organizers for possibility to participate in this conference. And today I will tell you about our investigation on Erbium and Ytterbium complexes, with which we deal during these pandemic years. I'm from Institute of General Inorganic Chemistry in Moscow. And this conference is dedicated to Professor Ivanov, which most of us know well. And just in January 2020, we just discussed with Konstantin about our joint work in field of EPR spectroscopy, and I already at that time I planned to visit Novosibirsk, but pandemic changed everything, and unfortunately we can't discuss anymore with Konstantin. So anyway, I go back to my presentation, and I will tell mostly about mononuclear complexes, because if we will consider polynuclear ones, or maybe some interactions, magnetic, we can spend all time of conference to discuss on this field. And so then we speak about single molecular magnets. We of course speak about materials for devices for memory storage and so on. And if we use single molecular magnets, in this case we can increase more than 100 times capacity of our memory storage devices. So, and main instruments which we used in our investigation is measurements in alternating magnetic field, and which allows us to obtain dynamic of magnetic properties of molecule. And in this case, we deal with 4 elements. And what do we deal with 4 elements? 4F elements. First of all, because they are placed on the bottom of periodic table, which means they have big number of electrons. And second, they have their own anisotropy. And after 2003, Ishikawa, a lot of person in the world in this field works with 4F elements. And in 2011, Jeffrey Reinhardt and Jeffrey Long published a joint and interesting publication in science, chemistry science. And now, as you can see, we can celebrate decade of this paper. And as you can see in green, they show us Kramer's ions. And Kramer's ions is most interesting for us. And in this case, we work with Kramer's ions. We choose Erbium and Ytterbium just because of they are Kramer's ions as dysprosium ones, which they have doubly degenerate ground state, and most promising candidate between mononuclear complexes. And Reinhardt and Long show us what, but they show us just selected single molecular magnets for that time. It's 10 years ago already, and between the selection, they show just one example of erbium complexes, which have quite big barrier of magnetization, relaxation, reversity. So, but they show us selected examples, and in 2013, scientific collective from Manchester show us they review which show us all known at that time examples of single molecular magnet at that time. And for Ytterbium, they show only one example. So 8 years ago, it was only one example. It looked like it was only one example of simple molecular magnet based on Ytterbium complexes. And you can see here what there is no Ytterbium at all. Dysprosium, holmium, Ytterbium, Erbium. And this picture was prepared by Nick Chilton, who is author. Authors put his name in acknowledgement to prepare this picture. And few years at the same year, 2013, Nick Chilton offers a simple electrostatic model for this determination of magnetization and entropy for dysprosium complexes. But he also can, if he wants to use his model, but replace some equations with erbium and Ytterbium examples. But most of all works with dysprosium, so he decided to use this model on example of dysprosium. So, and if you put such geometry of your geometry of orbitals, and it looks like you will obtain, and it's sometimes good correlate with real situation, you will have a good agreement with theoretical knowledge. And we done a detailed analysis of literature data on the single molecular magnets properties, investigation for erbium-based, mostly mononuclear Ytterbium-based complexes. And if you want to complete this field of research, you need to have a sandwich type of geometry. If you want to beat the records values, you need to have a sandwich type of geometry. And so, but in the case of Ytterbium complexes, there are a lot of possibility to obtain the best value at all, because there are not so much examples. For example, this one is our results. This most of the results shown here are it's our works. NCS, piperidine, phenanthralin, something maybe else. And you can work in this field, and right now we have some examples of Erbium and Ytterbium and complexes and its investigation. For example, if we deal with pyridine carboxylate, for dysprosium we have energy barrier height near 80 kelvins, and here we can see what for erbium complex we have there is my pointer. We have near 18 for dysprosium 80, for erbium 18, and for Ytterbium quite good for Ytterbium 55 kelvins. And which means, in this case, we have square anti-prismatic geometry as most of all acetylacetonates. So we can conclude what for erbium square anti-prismatic, and for literature data and from our data, it's not the best choice. But for Ytterbium, it's quite good result. And so we try to work, and we prepare a series of complexes with icyanate ligand. And you know, the first one, which put it in the left top corner, it was our initial compound, which we used for prepare all other compounds showed on this slide. And we can conclude what for Ytterbium complexes, it will be better to have square prismatic or square triangles prismatic bicapped geometry. But for erbium, we just can show what it's not the best choice. And so here we can see what if we have some kind of rigid ligands like phenanthralins, in this case, they prevent to obtain optimal geometry, and much more interesting results obtained for bipyridyl complexes, and the best from this one is just our initial compound. And so we decided what maybe we need to simplify our situation. I mean, if we have more simple situations, more simple complexes for Erbium, maybe it will be better. So here we have maximal results 50 Kelvin for Ytterbium complexes, and we work further, and we try to put the terpyridyl, which more rigid ligand and which have no so so freedom of to coordinate of central atom. You have some geometrical, let's say, geometrical limitation. So in this case, we obtain 29 kelvins barrier height. And but in case of p-peridyl, we just have this everything the same, just water molecules coordination and just simple p-peridyl, and the height of the barrier increased significantly. But you know, we think about a lot of such situation, and we want to know that time what we will observe in the case of just simple salt, which used aqua chloride of Ytterbium, which we used as initial complexes. And so in this case, what do you think about? Yes, in this case we obtain even higher value. So in the previous case 50 Kelvin, and here we have near 80 Kelvin for just simple salt from which you can buy from Aldrich or any there from. So it seems what if you simplify the system, you will obtain the higher value for Ytterbium. You need to just let's say you need to obtain yes geometry for optimal geometry for this type of Ytterbium electron density, but this type of electron density will be obtained if you have quite simple ligands. As for example, for dysprosium complexes, there are a lot of simple visperidyl and some alcohols and so on. And this is my point. What simplify system with Ytterbium will help you to increase energy barrier, or just simplify and be happy. And I want to thank Cryotrade Engineering Company for our helium regasifier, which was installed in December last year, last day, and December 31st, just a day before New Year, and now it's worked well. And it helped us to save a lot of helium, especially now in Moscow. I don't know how it's in all around the world, but in Moscow, due to pandemic situation, government bought a lot of tomographs, and helium cost a lot of money. Thank you, Cryotrade Engineering, for our reliquefier, and thanks my colleague for help in this work. Thank you.
Thank you, Nikolay. We have a few minutes for questions. Valentin, please.
Yeah, thank you for your talk. I wonder if these relaxation data are observed in zero field as well, or is it just field-induced SMMs?
It's just field-induced SMMs, and as you can see from work of Reinhardt and not Reinhardt one, but in Penny's group, Liefeld, what even said was just field-induced SMM.
So in that case, it means that you basically observed slow relaxation of magnetization in applied field. So basically you went back to the first works of Orbach actually, because back in the 40s of the last century has shown that simple halide salts of lanthanides have slow magnetic relaxation in applied field. So what is the difference then between your results and those which are like 90 years old?
Are you looking for difference?
Yeah.
Yeah.
Because it seems it was kind of the same compound. So it also was like dysprosium chlorine free, and you have Ytterbium chlorine free, and it also shows slow magnetic relaxations like it should. So what's different in comparison with what was reported many years ago?
Interesting questions. You know, I never think about it, what a difference. I didn't look for difference this case.
No, I'm just saying that it would be interesting to see if somebody back there described exactly the same compound like your record holding Ytterbium complex. Maybe it was already described, but just not measured in that much details like you did. It would be very fun to see. So
we'll check this moment, but nobody done it yet. If you know, let me know.
Yeah, I also check. I just mean that if it was published in 1935, probably it was not published as a chemical paper, so it wouldn't be really like it wouldn't have any crystal structure associated published as well. So it might be just in one of these early Orbach's paper because it had plenty.
Maybe. Thank you for comments.
Any more questions? Nikolay, thanks again. And the next presentation will be done by Boris Tsukerblat from Ben Gurion University of the Negev, Israel.
First of all, I want to thank organizer for the invitation to this nice meeting and for very good organization. So my talk will be devoted to the problem of new magnetic, maybe molecular materials for a special problem of quantum cellular automata. And first of all, I would introduce the people with whom we work on this area: Andrei Pali, Sergei Aldoshin, Denis Korchagin from the Chernogolovka Institute of Chemical Physics, Shmuel Zilberg from Ariel University, and Modesto Clemente from University of Valence. Since this topic is relatively new and not so popular in this conference, even that question is closely related with area of molecular magnetism and new kinds of technology, I want to make some introduction and to explain what is quantum cellular automata. The main idea of quantum cellular automata and molecular quantum cellular automata is to encode binary information in the charge distribution. We see that there is 4 points here, 4 sites, and 2 electrons that are distributed among 4 sites. And they prefer to have more distant distributions over the diagonals. And these 2 distributions are expected to encode binary information 1 and 0. And this is a way to encode information, is an exclusively classical way. This is not a quantum computer, this is a classical computer, but realized on very small object, quantum dot or molecules. From this elementary subunits, we can construct logic gates. For example, we have two cells, and in these two cells, the charges will be distributed, minimizing the Coulomb repulsion. So if cell 1 has encoded information binary 0, the second one will also encode 0. Then we can see that the first cell can be termed as driver cell and the working cell. If we put information or excitate or encode for driver cell 0, the unpolarized working cell accepts 0. This is a copy operation, and this was realized on quantum dot. And we can construct from quantum dot, from elementary cell, we can construct devices, logical devices. Let's say input cell has 0 information, is null, what people call null. Let's say we put 0 in polarized input cell. The next cell will be also polarized. The copy operation will continue. And at the end, we will go to the end, to the output cell to 0. And we see that this imitate quantum wire. Then we can construct fan out. We input cell is 1, output to output 0. And the process go here, minimizing Coulomb interaction. The same way in the same way we constructed quantum inverter that invert information. Input is 1, output is 0. And if we carefully see this area, we can see that the signal change inverse in this area. Then important majority logic gate, that is one of the important ingredient of quantum computer or electronic devices. This majority gate, if we put input, this output repeat majority of inputs, and we can see that this majority gate can be gate or gate and this is electronic, traditional electronic state. If we put different inputs, 3 inputs, A1, 1, 0. And this is a picture that's illustrated from Journal of Nanotechnology. People illustrate how this grids of or combination of circuits is constructed or designed, and this is remind some venomous species or sea snail. So, what is the real advantages of these devices? First, eliminates the need for current switches. Binary information is encoded in charge distribution. Then power gain, strongly reduce power dissipation and heating, because we could see that there are no wires, only Coulomb interaction governs this work. Then molecular size of and high density of devices and computational pipeline can be achieved by the very nature of OSA. Then the next productive, I would say, revolutionary idea was to construct these devices to design not from quantum dots, but from molecule. And we can see that the molecule, this idea, brings about several unavailable advantages. Like unlike quantum dots, the molecule can have specified chemical composition. They are absolutely identical. By chemical synthesis, molecular cluster can be engineered to have desired and controlled physical characteristics, and we can they can be attached to different types of platforms. These are several examples: tetraruthenium complexes, molecular metal L4 iron complexes that have square planar structure, then cobalt fragments. And the general feature of all these systems so far designed is that they use diamagnetic metal ions. And this is some kind of square planar mixed valence dielectronic cluster D1, D1, D00, 2 electron distributed over 4 spinless sites. And I want to show this picture to continue about advantages. This is a paper of Jean Marie Len, Nobel Prize. And he showed how to make special arranged grids on the surface. I will not speak about this, but I want to show only this picture. So the central idea of our work is to use magnetic ions instead of diamagnetic ones for design of molecular cells. And you see, this is a spinless core and 2 spin that can move around 4 ions, 4 spinless sites. What was a suggestion is to use paramagnetic ions. This is a purely theoretical suggestion because to realize it is necessary to have some synthetic efforts and chemistry or material science also. I show only some small mathematical excerpt, and then I explain in a very simple picture what does it mean. We introduce electron transfer, that is double exchange, Coulomb repulsion between electrons, special form of exchange interaction that act between the ions, because we have 6 spin, 4 localized and 2 delocalized, and vibronic coupling. And then let's consider more simple pictures, step by step, this interaction. First, Coulomb repulsion. Coulomb energy is a difference between the energy of neighboring configuration, 2 electrons are along the side, and distant configuration, antibody configuration, distributed or over diagonal. It's clear that Coulomb repulsion that is usually strong separates these 2 energy levels, and we will assume that Coulombian direction is very strong because we need 2 distant configuration. This condition is not necessarily satisfied in all cases, but now we assume about this. And the results that we can extend, as we can see, for simple system, for spinless cores, that is a subunit of the cluster we will consider, is that the ground state consists of 3 levels: spin singlet, spin doublet, orbital doublet, and spin singlet. The distances between these levels, the gaps, are approximately the same. And this is a case of strong Coulomb repulsion, and we will restrict ourselves only this simple picture. Then let's consider 2 interaction: electron transfer, double exchange, and isotropic magnetic exchange. Electron transfer is a transfer that occurs between the ions populated spin to the next ions. And we will consider the exchange interaction. Really, we have 3 exchange parameters: dn, dn ions, dn, dn plus 1, and dn plus 1, dn. But we simplify the picture and will consider only 1 exchange parameter. And here we have transfer. It is important to note that exchange interaction acts within each localized configuration. So we have several exchange interactions. Then I would little bit more attention paid to the double exchange that is in core of the system, in core of our consideration, and core of the phenomenon, physical phenomenon. The double exchange is spin-dependent electron transfer over spin core. This phenomena or this explanation have been proposed by Zener, Dejean, Anderson, and Hasegawa on their pioneering work about oxides, explaining ferromagnetic spin alignment. Let's say we have spin attached to ion, to certain ion, spin S0, and spin electron. Due to Hund rule, the spin localized tends to be parallel to spin of core. Then electron jumps to the second spin. Then if second spin in classical representation have some angle with respect to the spin of jumping spin take his direction. And then the spin of core tends to be aligned along the jumping spin. That's why we obtain ferromagnetic, really ferromagnetic interaction. And this transfer depends on full spin of the system. And we can see that this double exchange is always ferromagnetic because ground state is a spin with maximum spin. Normally the double exchange spin the isotropic exchange, but we can see that they will be should be taken into account at the same time. Exchange interaction, as I could tell you, acts within each localized configuration. Then let us look how two electron jumps. Two electron jumps are forbidden, and they really occur through the excited state in two steps. Let's say spin 1 jumps to the position 2 and aligns spin 2. Then spin 3 jumps to spin 4, to side 4, and aligns spin 4. And we have ferromagnetic interaction as it prescribed by the theory. As we could see, the ground state of the system of two spins is antiferromagnetic. And then spin at the side 1 and spin at the side 3 in the subunit, mixed valence subunit, are arranged in different direction. And they jumps and align the spin of core. So we have really antiferromagnetic effect, double exchange in tetrameric electronic system. Of course, this is each step is ferromagnetic by its nature, but the effect of the double exchanges and antiferromagnetic. Then we can go to the next step, the vibronic interaction. And here we will use the model that is dealing with the breaching vibrations as is traditional in quantum, in mixed valence system. This is out of phase breaching mode. Electron jumps, produce deformation of the local surrounding, then jumps back. The local surrounding moves out of phase, and this is a breaching out of phase mode. And this is a very well picture. This is the results. And in dymeric system, we can have three kind of potential curves, according to which the Robin and Day classification is formulated. We have strongly localized system in the case of strong vibronic interaction, partially delocalized system in the case of intermediate interaction, and fully delocalized system. And what is important is that the vibronic interaction produce strong trapping effect. Then we can see that in the tetrameric system, we have three vibrations according to the symmetry of the system. This is a picture that all surrounding have the same shape, is all normal coordinates are 0. This is a B1G coordinate, and this is a 2 coordinate of double representation, of double degenerate representation. Then we can see that by close analogy with the dymeric system, in tetrameric system, this B1G coordinate play rules out of phase mode. We can see the two localization are closely related to the potential energy in these two states, Q positive or Q negative, and this corresponds to two localization of the extra electron. And then we can see the effect of the vibronic coupling to the simple system. I will later show how this effect on the simple subunit, delocalized subunit, is interrelated with the more complicated results obtained for our systems that has 6 electrons. We can see the 3 levels. In the case of strong localization, give 2 localized configuration and paramagnetic ground states, because the spin triplet and spin singlet have the same energies. So this is an illustration of the trapping effect of the vibrations. And now we can go to the external quadrupole field that is important because we are dealing with the quantum cellular automata or devices in which the cell is not isolated, and the main processes that occur in these devices are due to the external quadrupole field of the drivers that govern the situation. First, I show the so-called very important characteristic of the devices, of the cells, is cell-cell response. This is a polarization of the working cell as a function of the polarization of the drivers. Polarization is the difference between the density of the mostly populated states minus the density normal as a density with the less populated state, electronically populated, I mean electronic density. This electronic density in mixed valence compounds is of course not 1 and 0, but they should be calculated by quantum mechanical calculations as a average, some averages using the wave function. And this is a picture that shows how the driver cell acts on the working cell. The adiabatic potential have equally wells equal in energy. Then when we put driver cell, one well becomes deeper and another, and this process determines the cell-cell response. Cell-cell response should be strongly nonlinear because the drivers, the working cell should fast reply to the the polarization of the working cell. Then the results we have obtained. The point is that we should calculate the energy levels and characteristics of this cell, of the magnetic cells in quantum cellular automata. Then we can see that this picture shows the ground manifold of the cell in the strong U limit, in the limit of strong Coulomb repulsion. This is a function of the U, some dimensionals U, and in the strong U limit, we have this manifolds of the level. And the ground state is as spin singlet state because of the physical reasons I show you before. Really, we have 2 electrons that are moving, keeping their spins anti-parallel, and they polarize the cell so that the cell fully is in antiferromagnetic ground state. Then, first, what I want to underline is that now, one point that I intentionally missed is that the B electron transfer occurs in two steps. First step excites the system. So we go from the distant configuration, first picture, to the excited configuration when these two spins, moving spins, extra spins, are at the neighboring side. And this has energy U. Then the next step also doesn't change energy, and we are in the excited manifold. Then we go to the ground state. And we obtain the Hamiltonian of the system. And from mathematical point of view, we make some projection operation that projects the full Hamiltonian of the system onto the ground manifold. So we are dealing with some parameters that is parameters t square divided by u. This is an effective double exchange parameter, second order double exchange parameter. And the second order double exchange parameter, of course, much smaller than the natural transfer parameter t. And in this respect, we can compare this reduced double exchange parameter with the normal magnetic exchange parameter in Heisenberg-Dirac-Van Vleck model. And comparing these two reduced double exchange parameters and normal exchange parameters, we can see that these values are of the same order. And we can see that the ground state is also magnetic. Then we include the vibronic interaction as a required necessary ingredient of the model. And we can see this analogy that I always already mentioned. Now we can see the diabatic approach to the system that illustrates simple thing. First, we can see the case of moderate or maybe weak vibronic interaction 150 with respect to 300 wave numbers, that is a frequency adopted. This is a parameters taken only to illustrate. There are not calculated values. And we can see that the ground state is as spin sync. Then when we increase the vibronic parameters and exchange parameters is almost zero, we can see crossover of spin levels, and we go directly from spin 0 to spin 3. The same spin crossover we can see in other cases. From, for example, in the case of exchange that is a little bit higher, 30 wave numbers, we can see ground state for weak vibronic interaction and spin triplet for spin vibronic interactions that is increased and gives rise to two localized minimum. Then, as is very well known, the vibronic interaction, the adiabatic picture loses its accuracy in the crossover region of the adiabatic potential due to fast Landau-Zinner transitions, and the nuclear motion cannot be considered as slow due to the fast jumps between the adiabatic curves. And in this case, we use quantum mechanical approach, and I fully omit the details. And we can have spin vibronic levels that also demonstrate how the vibronic interaction acts on the levels. And we see that the simple explanation that we got in the case of by the adiabatic approach works here also. This is on the exact vibronic picture. The three pictures I show here are important for interpretation. The three picture is the behavior of the magnetic sublevels with different spin multiplicity as function of the polarization working cell, as function of the polarization of the driver cell. And we can see the same behavior. We can see that the vibronic interaction increases, we have spin crossover of the levels. Then, using this wave function, we calculated electronic density, the wave function obtained by the solution of this on the spin vibronic problem. And we can see one important thing. First, we can see non-monotonic increase of the cell-cell response function. The cell-cell response function have steps, but these steps shows just spin crossover position of the levels and polarizations that induce the spin crossover positions. And this is important because we can have spin-dependent cell-cell response function. And second, we see that the vibronic interaction, the picture, right picture, makes some slow curve to be sharp. And this is an important role of vibronic interaction that is useful for creating of quantum cellular automata because we need fast response of the working cell to the field of the driver cell. Another important conclusion is that using the driver cell, we can manage with the spin of the working cell. And this possibility of the control of spin state of the working cell under the external action opens some new possibilities, new option for quantum electronics, not only for quantum cellular automata as the devices. So this is the main conclusions. And I can give some references on this subject that I collected here. So, and I want to acknowledge many grants that we got during the last years for this study. And thank you for your attention.
Vyacheslav, microphone is off.
Thank you, Professor Tsukerblat. We have time for one shot.
Yes, I am. Yes.
Jurgen Schnack.
Boris, very nice talk. Do you have an estimate how fast you can switch your automata? I mean, a normal computer runs with gigahertz, for instance. Do you think?
Sorry, Jurgen, I have not your question again, please, because
how fast can you switch your automata between the two different states? Do you have an estimate? Is that more megahertz or gigahertz? What is realistic?
I suppose that this is a normal frequencies for computer gigahertz. Mm-hmm. Should be gigahertz. And the role I want to, in reply to your question, I want also to underline that the vibronic interaction has some rules, positive, increasing the slope of the cell-cell response function. And the second, if this slope is the system is strongly localized, it cannot be turned between two configurations with the field of the driver cell. And this is some compromise is required to reach some position, some kind of vibronic interaction that is required for this, that is relevant to this problem. But better not to go to deal with the vibronic interaction is much better to work, at least to chemists, to work with the transfer integral, because they occur through the bridge, and the bridge can be controlled by chemical means or physical calculations.
Thank you.
Thank you. Thank you.
Thank you again, Professor Tsukerblat.
Thank you.
And the last talk of today's session will be done by Professor Oksana Koplak from Institute of Problem of Chemical Physics from Chernogolovka.
Can you hear me?
Yes.
Good afternoon, dear colleagues. How to say, last but not least, yes. The title of my report is Functionalization of monomolecular magnets using rare earth microparticles. But before okay, now will be better. Let me spend a few minutes to introduce my lab. Our laboratory, it's based in Institute of Problem of Chemical Physics in Chernogolovka. It's one of the biggest institute here, and our research topic it's molecular electronics, metal spintronics, and biomagnetism. Additional advantages our laboratory based on the research center of our institute, and we have very nice and modern equipment. So if you are interested in collaboration, we are open for new contact, for collaboration, and so welcome. If it's interesting for you, please write by this email. Today I will talk about single ion magnets or single molecular magnets. And their functionalization. It is well known that single molecular magnets are promising smallest element of magnetic memory. Additionally to promising application for the creation of high density magnetic data storage, chemically designed single molecular magnets are attractive for molecular spintronics, yes, and quantum computing, as today already told. The main conditions of the chemical synthesis of SMM or SIM is three main tools. It's symmetry, exchange interaction, and crystal field. In SIMS, the ion bearing the spin is most commonly a transition metal or lanthanoid, as you know, of course. Due to slow relaxation of magnetization, they are able to keep magnetization induced by external magnetic field during some time after such field is switched off. Most of the SIM complexes exhibit slow paramagnetic relaxation only in the presence of the external magnetic field, and the SIMs named called field-induced SIMs. And you can find a lot of links, a lot of paper in literature that described this phenomena in SIMs. In this case, we have big problem because the requirement to use external field of few kilohertz, it's the typical magnitude of DC field able to switch on slow relaxation of magnetization in such complexes. This intensity is not compatible with the strategy of the design of the low energy local memory elements, yes? It's a problem. And we find some new idea. Our goal here is to demonstrate that field-induced SIMs are not less attractive system for the design of elements of quantum computers or magnetic memory units than zero field SIMs, SMM. If we, instead of field generated by external electromagnet, one uses controllable internal magnetic field. In this work, we propose experimental technique which can be used to generate internal magnetic field in a composite material containing ferromagnetic rare earth micromagnets, it's microparticles, and powder of field-induced SIM complexes. We used hexa-coordinated cobalt-2 complexes as this formula. You can see the structure. More detailed and about crystal structure and the main properties of these complexes will be done by Igor Sherbakov in Wednesday at 1 p.m. Please welcome on his lecture. The nearest ligand environment, it's a first coordination sphere of these cobalt complexes. Ion in the considered complex involved for nitrogen atoms and 2 chlorine atoms. You can see this with green and blue blue marks. Crystal field produced by these 6 atoms gives rise to this hem of the 3D orbitals. This orbital hem corresponds to the ground orbital doublet of the quasi-octahedral cobalt-2 complexes. That is slightly split by the rhombic component of the crystal field into 2 orbital singlets, giving rise to the easy axis type magnetic anisotropy accompanied by weak rhombicity. It was our SIM complexes and source, magnetically hard source of the demagnetizing field. We choose these microparticles. This is hard magnets. Praseodymium, dysprosium, iron, cobalt, boron. It's family of neodymium, iron, cobalt, boron, and they demonstrate very high value of remanent magnetization and magnetization of saturation. Scanning electron microscopy data clearly indicates that these microparticles has micron size, first of all, and have round shapes with narrow diameter distribution. As I said, this permanent magnets is well known by its very high energy product, remanent magnetization and low temperature causticity exceeding 2 Tesla. It's so high. As you can see, this violet hysteresis loop demonstrate very high coercitive field up to 20 kilostat. It's 2 Tesla. This kind of microparticles has been chosen for the present study due to the very high residual magnetization. As you can see here, it's over about 600 electromagnetic units per cubic centimeters. It's so high, and this value too close to saturation of magnetization that equal about 700 electromagnetic units per cubic centimeters. But if we this is very high coercitivity hysteresis corresponds microparticles that was fixed in polymer matrix in ectosan. It's a non-magnetic one. But if we choose non-fixed microparticles, this shape slightly go to narrow, so smallest. But remanent magnetization still so high. Residual magnetization in zero field still remains very high. So for that reason, such rare earth micromagnets can be regarded as very good source for internal magnetic field. Okay. And we calculate this demagnetizing field by this very simple formula, and we estimate this value 1.2 kiloerstat in the vicinity of the surface of microparticles of average diameter about 5 microns, because the typical diameter for these microparticles. And you can see this same images and this some scheme, some sketch of our idea. And we hope that high enough to induce slow demagnetizing field, high enough to induce slow magnetic relaxation in SIM complexes. And what we find? We find that micromagnet free powder of cobalt 2+ complexes exhibits no slow magnetic relaxation at zero applied magnetic field, as it evidence from this orange line. No any signal in imaginary part of magnetic susceptibility. You can see on this figure, it's in left side of the slide. When external DC magnetic field was applied around 3020 erstat to this powder sample, two maxima in this dependence have appeared. You can see this red line and two maxima around 100 and around 4 hertz appears. This maxima indicating that such DC field induced SIM properties typical of the case when both intra and intermolecular relaxation mechanism are involved in the game. It is seen from the next figure. In the right side, that the dependence of the imaginary part of magnetic susceptibility recorded at the same temperature and the same condition for free microparticles, praseodymium, dysprosium, iron, cobalt, boron, in the absence of SIM powder, SIM complexes, shows no any peaks in split of the fact that microparticles have been preliminary magnetized in 5 Tesla magnetic field. But after we mix this two objects, microparticles and SIM complexes, the situation completely changed for composite materials of SIM powder with magnetic microparticles that was primarily magnetized during 5 minutes in the magnetic field 5 Tesla. So the dependence, as you can see here, the dependence of imaginary part of magnetic susceptibility measured for such composite sample at the 2K and the same condition, but in zero external magnetic field. And this dependence exhibits two peaks. I repeat, this dependencies was observed in zero external magnetic field for a composite that contains microparticles, magnetic microparticles, and SIMS complex. So it is notable that these peaks are well reproducible in the measurements performed for independently prepared composite samples. Also, the dependence of the magnetic susceptibility for the composite materials of the complexes powder with microparticles is similar to that recorded for pure complexes of cobalt, as you can see up and bottom. But peak positions are slightly shifted towards higher frequency. So it was questions why. This allow us to conclude that local internal field should not differ too much from 3.2 kilostat that we applied for the cobalt complexes. As we calculated, as you remember, in our case, it was 1.2 kilostat. On the other hand, the estimated value 1.2 kilostat clearly underestimated field intensity, because one peak only should be absorbed for such low DC magnetic field for these complexes. This can be explained by the fact that averaged local magnetic field of the magnetic microparticles depends on both residual magnetization and mutual orientation of magnetic dipoles affecting magnetic dipole-dipole interaction of microparticles, and on aggregation of seams and their distribution between microparticles. So it can be like composite. So all these factors can affect internal field and these dependencies of magnetic susceptibility peak position. Repeated magnetizing of the composite materials in DC field allow us to observe the effect of shifting of these peaks toward higher frequency. To avoid this effect, we have tried to prepare a new sample, the sample whose properties are independent of the magnetic prehistory. What we can do? We used polymer, again, this Eikozan polymer, non-magnetic one, for fixation. But in this case, we fixed microparticles with seams, this composite in polymer matrix. After the composite materials was fixed, AC magnetic properties becomes independent of magnetic prehistory. But in this case, such fixation results in shifted of the imaginary part of magnetic susceptibility to the high frequency range line out of the range of speed magnetometer. As you can see on the right picture, you can see this is maximum unvisible. He shifted in high value of frequency. Unfortunately, we have our speed magnetometer that can measure, that depends just up to 1.4 kilohertz. This can be explained by a coagulation of microparticles, which leads to the internal field enhancement, giving rise to the increase in the rate of direct one-for-one relaxation process. And on the slide, you can see the slow relaxation of these complexes in the presence of fully fixed microparticles, as I said. And you can see two types of dependencies. So one of them, it's field dependencies. This real part, it's a frequency, and we measured series of these dependencies from 0 field up to 5 Tesla. And you can see after 1 Tesla, one peak appears. But so it's invisible all. But when we are increasing the magnetic field, this delta here increase too. As you can see, this red line on the picture. And we we track this delta here. And right picture, you can see the dependencies of imaginary part of magnetic susceptibility at different magnetic field. And this tilt tail and this tail delta versus magnetic field goes bigger and higher and bigger. So we compare this data, and on the slide you can see a remanent magnetization of SIM, their field dependencies and dependencies of real part of magnetic susceptibility. As you compare, you can see these dependencies more or less the same, and it means that the magnetizing field is directly proportional to the remanent magnetization, and one can conclude that magnetic microparticles, their stray field can control over SIM spin levels. And main advantages of our work, if you can, I say, is control magnetic relaxation in SIMs in zero external magnetic field, where SIM sample does not manifest residual magnetization. So it's my conclusion. Most of them I already said during my presentation. If it was so fast, I'm sorry, but I hope that it was interesting. So I would like to thank you. Thanks Ministry of Science and Higher Education of Russian Federation. Thanks our colleagues, and thank you very much for your kind attention. Thanks.
Thank you, Oksana. That topic is open for discussion.
Yes, we have full of time.
Valentin, please.
Yeah, thank you. Very exciting results. So if I understood correctly, you pin you pinned your SMMs on the top of ferromagnetic material. So now you have non-degenerate levels for the ground state. So quantum tunneling is not an option anymore. But I wonder if it would be possible to magnetize molecule which is already on the top of ferromagnetic material, so it's magnetized in different direction, not to the same direction as ferromagnetic particle.
But it's a sphere. It will be interesting if we have some platform, some plate, some film. Yeah, I am completely agree. It will be very interesting. But we have a sphere, so now it's.
Yeah, but let's suppose you have a plane which is like this particle, but it's fully planar, and you have a molecule on top of this planar surface. And surface is ferromagnetic. So will it be possible to somehow change the orientation of the molecule without changing the orientation of magnetization of this ferromagnetic material? Or you have to switch both at the same time?
I think, yes, it can be possible, but we didn't it. But idea is, I think it can be work.
Okay, thank you.
The next question from Professor Tsukerblat.
I want to ask you first, this is a very elegant idea, and I accept my admiration about the idea. My question is, do you imply any condition on the size of the particle, magnetic particle? For example, can you use magnetic quantum dots for that?
It's our dream. We would like, because now it's just first step, and we see that its idea works. And now next step, we would like to choose smallest one, nanoparticles maybe, or quantum dots. So now it's just idea, but we hope we do it.
Thank you.
We'll do it.
Thank you.
I see one more question from Sergey Weber.
Oksana, thank you very much for a very interesting talk. May I ask you to show us slide number 8, please?
Please.
Yeah, this one. You know, I didn't understand. I'm sorry if you told about it, but I did not understand. So I would expect that this single ion magnets did not influence the magnetic behavior of your iron-based or dysprosium-based magnetic nanoparticles. Yeah. So therefore, in the figure on the bottom of your slide, I would expect a trace of the right figure on your slide. So do you understand me that I would expect overlap of two behaviors. So the first one is slow relaxation of your nanoparticles. And the second one is the slow relaxation, which this of single ion magnets, which was induced by these nanoparticles. But instead of this, we see only single ion magnets behavior, as I understand, isn't it? So where is the trace of your initial magnetic media dispersion of ferrum cobalt?
As you can see, so we have three situations. Yeah, first of all, it's just SIM. Yes, SIM in zero magnetic field and in applied magnetic field. Second one, it's a situation just for microparticles. And third one, it's situation for these complexes. If I understand your question, you understand for where effect from microparticles, yes?
Exactly, yeah.
So as you can see on the frequency dependence of magnetic susceptibility for microparticles, no any signals, no any peaks, just this very soft dependencies, yeah?
Yeah.
And value as you can see, value 0.2, and we think that this effect gives just in shift of these peaks, not in the peaks, but their position for their position.
So it means that single ion magnets somehow influence the magnetic behavior of microparticles.
Yeah, because we add intrinsic magnetic field.
Okay, thank you.
Welcome.
Oksana, do you have any thoughts about how your complex is displayed on the surface of the nanoparticles? Are there any chemical interaction, or it is just only physical absorption?
I think that it's like adhesion, so we have a lot of picture from electron microscopy and optical microscopy, and we see that this situation like here, so like shell on the surface.
Okay, thank you.
And I see that it's just put on the top.
I would like to help Oksana to answer Sergey's question and about microparticle background, gradual background, why this background not contribute to the final frequency dependence. This is a very simple effect. Frequency response of microparticles depends on their packing. And their packing depends on the powder which you install in between microparticles, because you increase the distance between microparticles and the frequency response of course changes. For that reason, we have very primitive effect, not interesting for research, just changing density of packing of microballs. We change this frequency response, and we not focused to study this gradual path, and we interested in just a single molecular magnet response.
There is a question from Nikolay Efimov.
Yeah, and I continue question of Sergey, and it's look like you need to measure this height at high temperature because according to lecture of not lecture on this conference, but Konstantin Zvezdin told what if you have particles, you anyway it's look like to obtain response from particles, you need to increase temperature because their magnetic moment and also relaxation, it looks like higher temperature, not 2 Kelvin.
But for these complexes, the temperature that where we can observe the magnetic relaxation is low, as you know.
Yeah, but if you want to look at the
Oh yes,
particles,
yes, all people want, not just we, not just me.
This complex do not work at high temperature at all. At high temperature, very rapid spin relaxation occurs and no chance to detect any frequency dependence.
Thank you.
Any more questions? If no, Oksana, thank you again for your nice presentation. It
Thank
was
you.
the last but not the least
Yes.
presentation of today's session. And now there is an announcement from organizing committee about poster sessions.
Yeah, dear colleagues, thank you, Vyacheslav, very much. Dear colleagues, in 10 minutes, we will start poster session. And I just say a few words about how it will be. So now I will open